Swayam Prabha. Digital India. Educated India.
Okay, so good morning everyone. So last class we saw that with 5 branching programs are sufficient to capture all of NC1, and as I said, like this was something that was not believed. In fact, it was conjectured that function like majority could not be solved by with 5 branching programs, and it's easy to see that majority is in NC1. So proving this, by proving this result, Barrington kind of refuted this conjecture. Okay. So now the question arises: what about smaller with branching programs? Okay, what about if we come below down to with 4 or with 3 branching programs? What kind of circuit classes do they capture? Is there any equivalence result corresponding to with 4 or with 3 branching program and some other circuit class? Okay, so that is what we are going to explore and see today. So we are going to see that so for with 4 branching programs no such nice characterization is known, but for with 3 branching program there is another nice characterization of in fact bounded depth circuits. So that is what we are going to see. So, and this result was also due to Barrington. Okay, so Barrington, after his result of showing with 5 branching programs are equivalent to NC1, he came up with this second result. So, we are going to focus on with 3 branching programs. Okay, and like last time we are going to look at this instruction model of looking at a branching program. Okay, so we saw that how if we have a sequence of instructions, how we can convert it into a branching program of the same length. So we'll a set of instructions over S5 basically corresponds to a branching program of width 5. Okay, so we are going to look at set of instructions over S3 instead. Okay, so before getting into the result, I will define a type of circuit. So a mod 3 dot mod 2 circuit is a depth 2 circuit having a mod 3 gate as output and mod 2 gates in the second level. Okay, and we denote the size of such circuits to be the number of mod 2 gates. Okay, so essentially it looks like this. So we have a mod 3 gate and there are several mod 2 gates that feed into it, and this is the input. Okay. This is the output. So, the inputs can have either variables x1 through xn, or it can have constants 0 or 1. Okay. So, this is what is called a well, AND OR gate can be simulated by a mod 2 gate. Okay. So, I mean this is how it is defined, mod 3 or mod 2. So, yeah, so by definition it does not have any other type of gates, AND or not, nothing. So, this is what this thing. So, the result is that we are going to see today is the following. So, this was also in 86 if I am correct, that let L be a language. So, L is accepted by a family of let's state this okay, a family of programs over S3 of polynomial length if and only if L is accepted by a family of mod 3, mod 2 circuits. Okay. So, this is what we will see. So, as I said once again that we look at the model where we consider the branching program to be a sequence of instructions over S3. Okay. So, each permutation is a permutation over S3, and the number of instructions is polynomial in the number of inputs. Okay. So, couple of lemmas before we get to the theorem. So, first a simple fact. Okay. So, if we look at these two permutations, so S3 is the symmetric group of order 3, and it consists of 6 elements, and if we look at these two elements, so G equal to G square, okay, 1, 2, 3, and H equal to 1, 2, 3. So, this notation means that, so this is the cyclic group of order 3, 1 is mapped to 2, 2 is mapped to 3, and 3 is mapped to 1, and this is the transposition which is mapping 1 to 2 and 2 to 1, 3 is mapped to itself. Okay. So, what can we say about these two? So, G and H generates S3. In other words, any element in S3 can be written as a product of G and H. Okay. So, now why are these two, why have we chosen? So, we can actually say something that is similar to what we said last time. So, if we look at the commutator, okay, so if we consider the commutator H G H inverse G inverse, so this turns out to be, I think, G, right, yeah, G. Once again it is very easy to check. So, if I take 1, 2, 3, 1, 2, 3, what is H inverse? It is H itself actually. Okay, because 1 is mapped to 2 and here again 2 is getting mapped to 1. So, it is its own inverse and G inverse is basically 3 to 1. So, if you actually solve this, this comes out to be 1, 2, 3 once again. Okay, so very standard. So, let me call this as theorem 1, call this lemma 2 and I will use a lemma 3. Okay, so this lemma is it's saying something about the output of a mod 3 mod 2 circuit. So, let C be a mod 3 mod 2 circuit of size S, then there exists a mod 3 mod 2 circuit C prime of size order S square such that for all x C prime of x congruent to 0 or 1 modulo 3. Okay. So, just a point that needs to be mentioned here. So, in general, okay, if I look at a circuit, if I look at a mod 3 dot mod 2 circuit in general, the output of this circuit can be 0, 1 or 2, right. So, depending on the number of ones that come into mod 3, if it is divisible by, I mean whatever is the remainder of that number when divided by 3 is the output of this circuit, right. So, okay, so let me put it this way. Well, okay, so mod 3 gate need not be defined that way. So, in general, so mod 3 gate is defined. So, if it is divisible by 3, it is 0. If it is not divisible, it is 1. So, that is one way to define it. So, then maybe I should state this a little differently then. Such that for all x, the number of ones that or the number of mod 2 gates that evaluate to 1 is congruent to 0 or 1 modulo 3. Okay. So, essentially what we are saying is that the number of ones that I have over here is only congruent to 0 or 1 mod 3. It will not be congruent to 2 mod 3. Okay. And that we can achieve by constructing a circuit C prime whose size is at most quadratic in the size of the original circuit. Okay. So, this proof just uses some number theoretic idea, essentially Fermat's little theorem. So, okay, let C1 up to CS be the mod two gates of C. Okay. So, each Ci, so we can write each Ci as so I can write it as Ci of x as 2 to the power a I 1 x 1 plus a I n x n plus C I minus 1 mod 3. Minus 1 mod 3. So, what are these AIs? So, where A I j is equal to 1 if x j is an input to Ci and it is 0 otherwise. Okay. So, essentially this is kind of counting. So, if I just look at this sum and Ci, okay, so I should also say Ci. So, Ci is equal to the number of ones into capital Ci. Okay. So, essentially what this power is counting is the number of ones that feed to the gate Ci. Okay. So, if a variable is feeding to that gate, then it is kept over here using this constant, and if a variable is not feeding to that gate, then it is turned off by setting that constant to be 0. Okay. So, it is essentially counting the parity, well, not the parity, but essentially the sum. Now, what is this, what does this turn out to be? So, if you look at any odd power of 2, okay, and you subtract 1 from it, what do you get? So, if you take an odd power of 2 and you subtract 1 from it, you get basically a number which is congruent to 1 mod 3. Okay. For example, 8 minus 1, 7 is congruent to 1 mod 3, 32 minus 1 is 31 is congruent to 1 mod 3, then next is 127 is again congruent to 1 mod 3 and so on. Okay. And if you look at any even power of 2 and you subtract 1 from it, it is congruent to 0 mod 3. Okay. So, this is again very simple, I mean you can prove it very simply, but essentially that is why we get this equivalence. Now, what we do is we apply Fermat's little theorem on this. So, by Fermat's little theorem, okay, so I need it. So, even before we get to Fermat's little theorem, let me just talk about the entire sum now. Let us just look at C of x. So, what is C of x? It is basically, I just count, I mean I just add up all these Ci of x mod 3. So, that will be sigma I 2 to the power AI1 x1 up to AIN xn minus S. So, S is the number of mod 2 gates. So, minus S mod 3. Okay. So, by Fermat's little theorem, what we have is we can write C of x as equal to the square of this mod 3. Okay. Or C of x is congruent to sigma 2 to the power AI1 x1 AIN xn minus S whole square mod 3, and right. So, yeah, I mean basically this follows because if, well, let's put this note over here. So, Fermat's little theorem. So, if A is not divisible by a prime p, then A raised to the power p minus 1 is congruent to 1 mod p, and of course, if A is divisible by p, then A raised to the power p minus 1 is congruent to 0 mod p. Okay. So, this is the first statement is essentially Fermat's little theorem. The second of course follows trivially, and that is what we are using over here. Okay. So, p for us is equal to 3. Okay. So, now we are taking, so this term is A for us. So, A square is congruent to 1 mod p. Okay. So, that is what we are using over here. And if A is not divisible by p, so that is if A is either 1 or 2, then we have that A raised to the power 2 is congruent to 1 mod p, and if it is divisible by p, which means that it is 0, then it remains 0. So, now once we have this, how do we get a circuit? So, essentially we can now expand the terms in the above equation and build a. So, essentially I will just look at this term and I just expand it out. Okay. So, I will get several terms over here. In fact, I will get order s square many terms. Okay. And because this is sum over s, so I going from 1 up to s. So, I get order s square many terms over here, and I just build mod 3 mod 2 circuit consisting of order s square mod 2 gates. Okay. So, this is all the toolkit that we need to prove our theorem now. Okay, so now proving the theorem. So, we will start with the reverse direction, that is, given a mod 3 mod 2 circuit, how do we get a sequence of instructions that accept the same language. So, let C be a mod 3 mod 2 circuit. So, first how do I represent a mod 2 gate? I mean, how do I represent a mod 2 gate as a branching program or as a program over S3? So, what is the, just think about it for a moment. So, what is the obvious way to do it? So, what do I want over here? What I want is that if the number of ones coming into that gate is odd, then it should be odd, and if the number of ones is even, then it should be 0, right? Huh? So, I want a sequence of instructions over S3, right. So, what kind of instruction, and these instructions will be permutations over S3, okay. So, suppose if I have a variable, okay, so let so if it is 1, then I flip it somehow, right. So, what is the permutation that corresponds to a flip? It is basically the permutation H, okay, it is basically the transposition, okay. So, if it is a 1, then I will apply H, and if it is 0, then I apply identity, right. Now, I just count. So, if the number of ones is even, then basically H to the power an even number is identity, and if the number of ones is odd, then H to the power an odd number is H, okay. So, it basically H recognizes this instruction. So, that is essentially the idea. So, okay. So, for a mod 2 gate, okay, say G, if Xi is an, let me not use G over here because G is used in a different context. Actually, I do not need any notation for this right now. So, for a mod 2 gate, if Xi is an input to the gate, then add the instruction okay, let me do it a little differently slightly. Write it as a table. If I have Xi as an input, then I will add the instruction I H E, and if let us say a constant 1 is an input, then what should I add? So, what does 1 do to a mod 2 gate? Huh? It flips the value that is computed so far, right. So, what should I do? Huh? It should be H in both cases. So, whatever it is, it should get flipped, and 0, it is identity, it does not matter. I mean, we can just keep it for the sake of completeness, it does not change the gate. Okay. So, this is how we handle a mod 2 gate. Now, the point is that so for a mod 2 gate I have a program. So hence we get a program that H computes a mod 2 gate, right. So, now what we will do is that I want to say that I mean I want to get a program that would also G compute a mod 2 gate. How can I do that? So, now I will apply lemma 2. Okay. So, what? What is the number of mod 3? So, the number of mod 3 gate is 1, there is only one mod 3 gate, and the number of mod 2 gates is polynomial. So, S is polynomial in the number of inputs. Okay. Well, yeah, it is not. Okay, maybe I can just write it over here by a family of mod 3 mod 2 circuits of polynomial size. Yeah, so you are right. So, yeah, if you do not mention it, it can be more as well, but yeah, so we take it as polynomial.